Hello everyone, this is TSS Zindabad and today we are going to discuss the daily challenge of Leetcode. The question is amount of time for binary tree to be infected. So let's jump into the problem statement. It says that you are given the root of a binary tree with the unique values and an integer start at minute 0 and infection starts from the node with value start. Each minute a node becomes infected if the node is currently uninfected. Second, the node is adjacent to an infected node. We need to return the number of minutes that are needed for the entire tree to be infected. So let's understand the problem statement. The problem statement is saying that I will be given something like this, a tree, and I'll be given a start value. We need to understand that we are not given with a tree node, we are given with a value. So I need to make this note that I need to figure out which node corresponds this value, right? So this is one point. So after that, the other thing that we need to understand is that we want the infection to be spread all over the tree. That means all the nodes in the tree should be infected. And how it can be done? Only if a node was not already infected. And the second is it needs to be adjacent to an infected node. Let's talk about the approach, that how will I tackle this problem and what all things do I need to keep in my mind while I'm solving this problem if it comes in an interview. Okay, so the first thing I understand from this is that it looks a bit similar to something that I might have already done. So if you know what are graphs, this question would be very easy for you to solve, because in graphs we have almost a similar structure, right? But the storing is different, right? Right now we have a tree. So in a tree, what happens is whenever I talk about the traversal, right, I can go to its children. So in a tree, we know we have a parent and we have children. And there is only one way direction, one way movement, right? We can always go from the parent node to the child node. And when we talk about the binary tree, we have two childs, that is the left child and the right child. I hope that is clear. Now let's compare it with graph. In graph, we have two different methods for storing the adjacent nodes. That is the adjacency matrix and the other one is the adjacency list. So why am I talking about graph in a binary tree problem? I am pretty sure a lot of you are thinking about this. I am talking about this because this question completely replicates a graph concept. Just the only difference is that, as I told you, in a tree, there's only a one-way movement from parent to child. But in a graph, in an undirected graph, right, we can have it in two ways. That means the parent can also communicate with the child and the child can also communicate with the parent. So I understand that when we talk about infecting the adjacent nodes, so we need this concept. Now, why do I need this? I need this because let us assume this node, which is in blue color, is the infected node. So that means this is the start node, right? We already know the root node is 1. So after figuring out this node, I understand that if I want all of my tree to be infected, then its adjacent node needs to be infected too, right? So what are adjacent nodes? Adjacent nodes are the one which are connected directly. So we can see that 3 has a direct edge with 10, it has a direct edge with 6, and it also has a direct edge with parent, that is 1. So if it was a graph question, it is very easy to implement this. But when you talk about trees, as it is only one way flow in the movement, the question comes is how will we go to the parent? Because we've understood the fact that we need to go to the parent as we have to visit the adjacent nodes, the all adjacent nodes, which are currently unaffected. And while doing that, I have to return something like a time. That what time will I take so that all of these nodes become infected. So to tackle this question, what we can do is, if I can have something like a mapping, right? If I can have a mapping that will store the parent and the child. That means, for example, through any tree traversal, it can be any, you can either go for BFS, that is breadth first search, or depth first search. Using any of these two traversals, you can form something like a mapping in which, if this is the node, it is storing its corresponding parent. Now, why this will work is, it is mentioned in the question that the values are unique, right? So we can use a map. That means this is the key and the value. So there would be a unique key always. The value can be duplicate, it does not matter. The key needs to be unique. So I can say that for 3, the parent is 1. For 10, the parent is 3. For 6, the parent is 3. For 5, the parent is 1. For 4, the parent is 5. For 9 and 2, the parent is 4. And I can store it somewhere like this. And when we talk about the root node, we can simply have something like, for 1, it is -1. And we can handle this separately. So I've understood that if I can have this mapping, I can easily convert my tree question into a graph question, because I'll have a two-way flow, which is required when I talk about the adjacent nodes. Now, when I talk about the adjacent nodes, let me quickly copy paste this image down. Now, when I talk about the adjacent nodes, that means if this was the start node, I want that this is infected at time 1. This should also infect, right? These 3 nodes should also get infected. That means at time is equals to 1, because this was at 0. It is given in the question. So all of this should be 1. Then after this, as they do not have any further nodes, that means 10 and 6 are leaf nodes, so do not have any children. I go to 1 and I see, yes, it has a child. So this should get infected at t is equals to 2. 5 has a child 4, it gets infected at 3. And 4's children, that is 9 and 2, should get infected at time is equals to 4. And my final answer should be 4. Now, when I talk about this whole concept, what comes into mind? Aren't we having something like a level order traversal, where I'm trying to figure out all those? If I could replace T with a level, that means level 1, which all nodes are connected with this node, the first level, the second level, right? I'll quickly draw it here. The first level, the second level, the third level, and finally the fourth level, right? So I can understand that we can use something when we talk about level order, that is breadth first search, in which we'll be using a queue data structure, and further we'll be solving the question. So we've understood the fact that we need to have, the first thing is we need to have a mapping, right, between the parent and child. Second, we know that for finding the answer, I need to follow the breadth first search traversal, right? But there is one more thing that we need to take care. If you have done some questions on the topic of graph, you know that whenever we are visiting another node, we always have to check that is it visited or not. And this hint is also given in the question. Here in the first point, they have mentioned that the node is currently uninfected. So what we can do is, we can simply keep the third step. The third thing that we need to keep in our mind is, we can simply keep something like a visited data structure for keeping a track of which all nodes are infected and which are not infected. And through this, we'll get the final answer. So this is the approach that we will be following. Now, we have talked about the approach. Let's see if this approach actually works, or is there certain modification we need to perform. So I'll be using the similar example. Let's go to the clear screen. Yes. So I'll quickly copy paste the three things that we have talked about. So these are the three things that we want to achieve, right? So it says that we need to have a mapping, we need to have a visited data structure, and we need to have a BFS traversal. If you remember at the starting, I told you that we have been given the value in the question. We are not given with the node itself. So one more thing that needs to be added here is we need to find the start node, which corresponds to the start value. Okay. So these are the 4 points that we need to take care. Now, using these 4 points, I'll quickly do a dry run for us to understand that what is happening and is this what is required. So, assuming we have something like a main, right? In main, the first function that I need to call would always be the mapping, right? So let's call it parent to child. This is basically, you can have an map data structure, right, which will be storing it. So that means and this can be implemented either using breadth first search or depth first search as mentioned before. So let us assume that I am having something like a breadth first search for this also. So here I'll have a mapping which is saying that node and parent. So 3's parent is 1, 10 and 6 parent is 3, 5's parent is 1, 4's parent is 5, and 9 and 2's parent is 4 and 4. And for 1, we have -1 because that was the root. It does not have any parent, so we'll put -1. After getting this mapping through this function, right, I write here function. Through this function, what next do we need to do is, now we need to figure out where is the start node. So as to figure out where is the start node, we can again write another function, right? Which can be something like a find function in which I'm simply passing the root and the start value. Always remember this is an integer value in the given question. It is not a tree node value or a pointer. Okay. So after this, let us assume I have got a pointer. It is somewhere stored in a pointer, right? And let us assume its name was st. So that means now everything following this I have to work with st pointer, right? I am no more using root. I'll be using a st pointer, which is giving me which is the start node in the whole tree. We'll be talking about how we'll be implementing both of these functions in detail when I'll be coding it out, right? So after figuring out the mapping, then figuring out what is the start node, I need to implement the BFS. But before implementing the BFS, as I've mentioned before, that it is vital to have a visited array. So we can simply have a visited unordered map, right? So this is not the syntax what I'm writing here. I'm just simply writing for you to understand that these things are something we need to do, right? But I'll still write it in a manner so that it's easier. So here we'll write visited and rather than let's write bool. So here we can add the tree node or the value of it because it is unique, so it works either way, right? So if you want, you can even add the pointer here or the value would still work. After all of these things, the next thing that I need to do is I need to implement the breadth first search. So now when I talk about breadth first search, I'll be writing it here, right? So when we talk about this was first, second, third. Now when I talk about the breadth first search, I need a queue data structure, right? So what I'll do is I have this queue data structure and in this I'll simply push my start node. After pushing it into my start node, I can have a visited, right? So we'll say that in visited, the 3 has been visited. So for this simplicity, I'll be just sticking it here, right? So that means I've visited 3. After visiting 3, as we know that Q is a first in, first out data structure, I'll pop out 3 and I'll see that which all are its adjacent nodes. Now, when I say adjacent, like in general BFS, we used to just figure out in the case of trees that does it have a left child or a right child, and then we used to push it into the queue. Here, as we're talking about this problem in which we need to work with adjacent nodes, we need to figure out the left child, the right child, and the parent. We know how to get the left child and right child. That's the conventional way of doing it. And we have found the parent where? In the first point, that is the map between the parent and child, right? So here I can simply see is that yes, we can add 1, and let us suppose that for it to be easy, what I'm doing is I'm also adding a time value, right? So that we do not have to recompute it every time. So initially it was 0. Now 1 is added, the parent, and whatever is this is the node, and this is the time. So whatever is the time, just plus it, because we know that we're going to the next interval of time. So 1, 1, 10, 1, 6, 1. Now, what does these three things basically showcase? It shows that node 1, node 10, node 6, all of these nodes simultaneously at time is equals to 1 get infected, right? So, I have marked these. Now, after that, I'll again move to the next one. Here, I'll pop out 1, comma 1. I'll visit it, right? Now, after visiting, what I can do is I'll simply, and there's one more thing that you always need to remember is that before you are pushing it into the queue, you need to check that whether it is visited or not visited. If it is visited already, you skip it. If it is not visited, only then you will add it, right? So here, now 1, comma 1 was visited, 10 was visited, 6 was visited when we were adding it into the queue, right? You can do that either ways, right? The statement can come either way. Now, what I'll do is I'll say, okay, do you have a parent? It'll say no. It is -1, so I do not have a parent. That's okay. Do you have a left child? It'll say yes, I have a left child. So here the time was 1, the time will increment to 2, and 5 will get visited. Now after this, there is no other child. The right child of 1 is 3, and that has already been visited. So I cannot revisit this, right? So I'll simply skip it. Now after this, what I'll do is I'll pop out 10 and I'll ask 10, do you have any parent? It will say yes. So what is your parent? 10 will go to this mapping and we'll see that 10's parent is 3. Now I'll go to the visited part. I'll say, oh, but 3 is already visited. So I do not have to do anything. I'll simply skip 3. Now I'll ask 10, do you have a left child? So no. Do you have a right child? No. So we were like, okay, let's move forward to the next element in the queue. We get a 6. Now when we get 6, we say that what is the parent of 6? We get 3. Again 3 is visited, skip it. Has left child? No. Has right child? No. So we move to the next child, that is 5, 2. When we get to 5, 2, we see, do you have a parent? So 5 says, yes, I have a parent, it is 1. I'll go and check it. Is it visited? It is visited. So just skip it. We'll say, do you have a left child? No. Do you have a right child? Yes. Add it into the queue and increment the time by 1. So after that, we go to 4, 3. When we are here, we'll say 4, do you have a parent? We'll say yes. Which is your parent? It is 5. But 5 is already visited, so we'll not revisit it. Let's skip it. We'll say, do you have a left child? It will say, yes, I have a left child. Add it into the queue and increment the time. With me, it was 3. For my child, it will be 4. Do you have a right child? Yes. So 2, 4. After that, this further continues. We get 9, 4. We'll say 9, which is the parent. It will say 4. It is already visited when it was added. So what we'll do is that 4 will not be added again, right? It does not have a left child, does not have a right child. We go to 2 comma 4. We said, do you have a parent? It will say, yes, it is 4. We'll say, but 4 is already visited. So let's move forward. Let's skip that part. And we'll say, do you have a left child? It will say, no. Do you have a right child? No. So in this manner, we have exhausted the queue. And we can keep something like a variable, that is time, which is storing the end time, right? And we'll get 4 as the answer. So I feel the approach should be quite clear to you, right? There are 4 steps that we are following. I'll quickly write them up. The first one is the mapping between the parent and the child node, right? And for that, you can simply use unordered map data structure, right? Which can have the pointer and pointer, right? So that we can have the node that can be tree node star, whatever is given in the class. The second thing that we need to do is we need to have a visited array, right? Basically, in this case, we need to have a visited map, we can say, in which we are storing either the pointer or bool, or even we can store the integer value because it is unique, so it works either way, right? Then the third thing that we are going to do is, as I mentioned before, we have to figure out the start root. That means we need to figure out the start node and then we need to use it all throughout. So for that, we've utilized a find function, which we'll be making, right? It can again follow any traversal. It can be the depth first search or breadth first search. It works in either case. And the fourth thing we need to do is we need to implement BFS using a queue. So these are the 4 steps that we are going to follow. Okay, so this is the problem. Let's code it up quickly with the approach that we have formed. So I'll have the unordered map for storing the mapping of the parent and child. So it would be tree node type, and let's name it child to parent, and let's call the function, let's call it mapping, and we'll pass the root and we'll pass the unordered map that we have just created. Now let's first of all write this function. This function will not be returning me anything. It will simply fill this mapping with the child nodes corresponding to their parent nodes. So let's copy paste it here. So what I'll do is I'll be utilizing BFS. You can also use DFS if you want to. So for implementing BFS, I'll quickly use the queue data structure. I will push the root and I'll say while the queue is not empty, so that we can move forward with breadth first search. I'll say let's have something like T, this queue dot front, queue dot pop. I'll pop out whatever the start node is, and I will say that if the T has a left, that means the temporary node that T has a left. So in that case, what you need to do is in child to parent, I want you to store the T left child having T as its parent and push the T's left child into the parent, into the queue, sorry. And I'll be using it in the same way for the right child. I'll quickly change left to right here, and it is done. I have stored the mapping. That means the child, the left child is storing the parent, the right child is storing the parent. So after doing the first step, the next step that I need to do is I'll simply create the unordered map in which I'll have the tree node star and boolean as the template. Now, why do I need a visited? Though, it's a very common question that in trees we do not need a visited, right? Why do we need it here? We need it here because we studied that tree generally are one-way directed. That means there is a flow from parent to child. But here, as we have also computed one more flow, that is, we can even go back to the parent. So we need to keep a track so that we do not get stuck in an infinite loop. So that is why I'm creating this visited unordered map. The third thing I want to do is I want that I need to figure out which is my starting node. So what I can do is let's have the tree node star as st and let's call a function find which says I need the root and I need the start. So let's create the function here. It will give me the tree node star and its name is find and it has the same parameter. So let's quickly copy paste it here. So now I can, for finding the route that we require, we can use any traversal, breadth first search, depth first search, and further in depth first search, we can use any one that is required. Here, I'll be using the pre-order traversal. So let's write the base case that in this case, you need to return me a null. And if the root val at any point of time, it is equal to the start, then you return me the root. Else, if the root has a left child, in that case, form a tree node star and say it to be left, right? And we will call the find function. We'll go to roots left and start remains the same. If root is, if root has a right child, then go for tree node star R and call the find function, go to the right child and start remains. If R exists, then we'll return R. And here also, we can do the very same. We'll say if L exists, then return L. Now, I have made the mapping between the child and the parent. I have created a visited array. I have found my starting node, which is already in fact the time is equals to 0. So now I'll make a queue for implementing the BFS. I can have something like the pair, right? So the pair will have the template of tree node star and it can have the integer value which will have the time. So here what I'll say is I'll say, okay, push the st and at it is pushed at time 0. At that very same time in the visited, mark st as 1 that we have already visited it. So we'll say while queue is empty, while queue is not empty, I'm sorry, what we'll do is we'll say tree node star temp is equals to queue dot front first, that is the node, and we'll say int time is equals to queue dot front dot second, right? And we'll just pop it out. After popping it out, first let's do the conventional way, that is the left child. So here I'll say if there is a left of the temp, then in that case what you need to do is you need to push it into the queue, that means temps left and whatever was the time of temp plus 1. We'll do this similarly for the right child also. So let's write right here. So yeah, and then now we will do the, now we need to figure out the parent, right? So that is the parent utilized or not. Now, if anybody of you was paying a little bit attention, would have noticed that we have not utilized visited, but it is of utmost importance. So let's quickly add it up here that we'll say that we can only push it if that is not visited yet. So I'll quickly add up this condition here as well. It's a very important condition. I've already explained why, because we do not want to get stuck in the loop again, in the infinite loop. So what we'll say is, now for parent, we'll say that if the child to parent has a value corresponding to temp and it is not visited. This is not visited. Let's put a not sign here. Then in this case, just push whatever you have in the mapping and increment the time by 1. So this is done and we need to return the total time. So we can say is equals to the time and we can return. I think we're good to go. Let's see. Okay, there's an error in line number 50. I'll do it. I'll simply remove this if condition. Why? Because the start value will be there, right? So we can figure it out here. I guess this should work now. Let's see what happens. Okay, time limit exceeded. Let's see why. Probably here something. Okay. So while you're pushing it into the queue, it is very important for you to mark these nodes as visited also, right? So that is why we were using visited. Let's quickly add it up here. I'll say, right. See, debugging is very important. Understanding how to debug your code. Writing code is one thing, but knowing how to debug your code is the ultimate thing, right? So let's quickly do this and see if it's working fine now. Okay, I did not put the semicolon. Okay, looks like it's working fine. Let's submit the code once. And yeah, it's working. So that's great. Now, it's working. Now let's quickly take this code and understand the time and space complexity. Okay, so now let's discuss the time and space complexity. When we look at the code, there are certain things that are very clearly visible here, right? The first thing that we did was mapping, right? I hope you are able to see the code here, right? Right. So you see the first thing that we did was mapping. So this is the first thing. Let's go to the mappings code. Here we can see that I am going to BFS. Now in BFS, I am going to every node to figure out its parent, right? I want to know every node's parent. So that means I'm traversing every node. If there are n nodes in a tree, I am going to all of them. So the time complexity becomes O of n because I'm visiting all of them, right? After mapping, the second thing that I'm doing is I'm forming a visited unordered map. We'll talk about this later because this is related to the space complexity. Then I'm going to the find function. Let's go to the find function here. I can see I'm again using a DFS and here the worst time complexity can again be O of n, where n is the number of nodes in the tree, right? For example, there was a start node which was a leaf node, right? So you have to travel all of them. So the worst time complexity turns out to be O of n. After that, what I'm doing is I'm implementing a queue. Right here, I'm implementing the breadth first search. So again, that will be O of n. Therefore, I can see I have a time complexity of O of n plus O of n plus O of n. That is 3O of n, which is again equal to O of n. So it's a linear time complexity. Talking about the space complexity, as we are having two unordered maps, one is the mapping one and the other one is the visited one, and it is storing all the number of nodes that are there. So the space complexity turns out to be 2O of n, which can be considered as O of n only. Hence, the time complexity and the space complexity is O of n. Thank you so much for watching the video till the end. Please like, share and subscribe. Thank you.